Homework 2. Now, before we get started, I want to point out that the thermodynamic table of values, the standard values that are in the classroom, are also embedded into this homework assignment as well as your quiz. So if you scroll down at the very bottom, you have your periodic table. But here we have the standard thermodynamic table that is found in the classroom. Now, this table is updated periodically, so it's possible that in this video, the values used on this table are going to be different than the values that you see in your classroom. Use the values that you see. The table is updated as more recent data is made available and accepted. Question 1. You are asked to define one of the following. You get a choice with the homework, but for the quiz, you will be told which one to define. So if you define entropy, make sure to make a collegiate level definition, include the laws of thermodynamics that are important. One of the definitions is the second law of thermodynamics. So actually you could cover two birds here. If you define spontaneous and non-spontaneous processes, make sure to use an example. In fact, you should use an example with entropy as well. How would you use an example for a spontaneous versus a non-spontaneous process? Well, you would probably give me the signs of entropy and or Gibbs free energy, or both. For Gibbs free energy, I'd like a definition. In fact, it's asked for in your lab as well. So again, two birds with these definitions. So make sure to get a well thought out, well structured definition for any of those for the homework. Number 2, calculate delta S at 298 for the following changes. Here we have copper gas or solid copper moving to copper gas. Well, the delta S that we would be looking for is the values that are found on the table. So we're going with the change in entropy is going to be equal to the sum of the S of the products minus the sum of the S of the reactants. In this case, the product is copper gas. So I'm going to go down here to my thermodynamic table, and this is in alphabetical order by primary element. So I'm looking for copper. It shouldn't take but a second to scroll down. And here's copper. So copper gas, I'm looking for the S, the entropy, and that's over here in the last column. So 166.38 is the value. So that's the product, 166.38. And I'm going to subtract from that the value of my reactant, 33.15. That's copper solid. And I get a value of 133.23. The units for that are joules per Kelvin per mole. Now, because we use the mole value, the stoichiometric value, a lot of times when you see the delta S, you'll see it just as J over K. Now, for our system, what I need you to report is the numerator. We come up here. I'm looking for question 2. I would type in 133.23, and that is positive. Number 3, we're going to calculate the delta S 298. For this is a slightly more complicated. Now, I do have some narrative here. Now, you may be given a reaction using names. For example, you could have been given solid zinc reacts with copper 2 sulfate to produce solid copper and zinc sulfate. So you may need to review how to make chemical formulas from names. So what we'll do is look up, in order to find our delta S, we need the S of our products. So I need copper and my zinc sulfate. And then I'm going to subtract the S of my reactants, so zinc and copper sulfate. Now, I happen to be on copper already down here. Scroll down again. So solid copper was 33.15, so I will put that here. And copper sulfate is down here at 109.2. Then I need to go to zinc. Again, this is in alphabetical order by primary element. So I'm going to be all the way to the bottom. There's zinc. So solid zinc is 41.6. That's a reactant. And then I have my zinc sulfate, solid zinc sulfate, 110.5. So I'm going to add these two and then subtract them. So these are the values I get. I get overall for the reaction, I get a delta S of negative 7.15 joules. Come back up here. When you have a box like this, I just want you to put the value, not the unit. You will usually be told to what place value to report your answer, but in this case, that's all we get is 7.15. Now, I do have these little reminders here. So show as much work as you have time for. If you don't type in your work, submit your work in the accessory quiz, and I'll show you where that accessory quiz is in a different video. So question 4, we're going to calculate all of this information. What we're going to find is the delta G, and for some reason my little not values have disappeared, but we're going to calculate our delta G, our delta H, our S. We're going to identify is the reaction spontaneous at 298. What temperature would make this reaction change the answer to number 4? And what's the delta G value at this temperature? Well, in order to find these G values at 298, what I'm going to do is look at my table of values. So I need my reaction, my NO2 and my N2O4. So now I'm looking at nitrogen. I'm going to go to my table and I'm going to just copy those values down real quick because that's going to make this faster for me. So I need N2O4 and it's a gas located right here. So I was actually able to copy and paste for this exercise. I know you're not going to have that capability necessarily, but what I want to do is first show you, so this is H, this is G, and this is S. So to find the H value, what I'm going to do is take the sum of the products multiplied by the stoichiometric value. So my 2, well, I can't work within a table. So 2 times my product value, 33.2, and then I'll subtract my reactant value, 11.1. The units here, these are kilojoules per mole. These are also kilojoules, but these are joules. So I'm going to just work this out quickly here. I use the same structure, 2 times my product minus my reactant. And for this as well, 2 times my product minus my reactant. So these are the values I get. I get a delta H of 55.3 kilojoules, a delta G of 2.8 kilojoules, and a delta S of 175.8 joules. So I type all of those answers in here. Now, is this reaction spontaneous at 298 K? What I found with all of these standard things is that no, it is not, because my delta G value is positive. That means this is not a spontaneous reaction. At what temperature would make this reaction change the answer to number 4? So at what temperature would we be spontaneous? Well, in order to find that, I need to use the G equals H minus TS equation. And then I set my G equal to 0. I fill in my H at 55.3, and remember this is kilojoules. I don't know the temperature, that's what I'm solving for, and then I fill in the S value, but I have to convert that into kilojoules as well. So now I solve for the temperature that I do not know. Divide both sides by 0.1, oops, I have 2 decimals there, by 0.175.8. And I get a temperature of 314.56 K for Kelvin. And I'm looking through, and I only have 3 sig figs for most things. I'm going to leave this at 3 sig figs, and I'm going to call that 314 Kelvin would change that answer. Now, what's the delta G value at 425 Kelvin? Well, in this case now, I know my T. What I don't know is my G, but I'm going to use this equation again, except I'm going to fill in 425 for Kelvin. And I get a G value with this of negative 19.415. Again, with that decimal, I'm not sure why that keeps creeping back in. So we would report this with 3 significant digits because that's really what we have going. So I would call this negative 19.4 kilojoules. And then I would put this at negative 19.4 kilojoules. Make sure to tell me kilojoules or joules, even if you leave the mole part off. I need to see these answers on your quiz, even if you're going to upload your work with the accessory quiz later. Number 5, we're going to use the standard free energy of formation data in our thermodynamic table in order to determine the free energy change for this reaction here, and it's run under standard state conditions. So all we're looking for here is our G values. So in order to find our delta G, we need to take our products. So I'm looking for CCl4, and I'm going to add that to the G value of S2Cl2. Then I'm going to subtract the values of my reactants. So that's going to be CS2, and I'm going to add that to 3 times my Cl2 value. So I come back over here to my table, which is found at the end, and I'm going to start by looking up CCl4 and CS2. So I'm going to look at carbon. So CCl4, carbon tetrachloride, and I have liquid and I have gas. So I need to pay attention to what the question was asking. The question has gas. So I need to make sure that I'm using the gas number. Carbon tetrachloride gas, delta G is the one in the middle, so negative 58.2. Now I need CS2, carbon disulfide. Carbon disulfide is here, so 66.8. Now I need chlorine. Chlorine gas has a 0. It is at its standard state. Chlorine gas is the elemental state. So now this disulfur dichloride is probably going to be in sulfur. So S2 S2Cl2. I have a liquid and I have a gas. I need the gaseous form. And it's a good thing I need the gaseous form because the liquid doesn't have a delta G associated with it. So we have a negative 29.25. So now I'm going to add these things together and then subtract them. And overall, I get a negative 154.25. Now the units here are in kilojoules or kilojoules per mole. So I'm going to scroll back up. How are we going to insert this? We're going to just declare it. The G value is 154.25. And it says to type in my or show my work. So you can show your work here, and it could be as easy as this. Just like that. That's really all of the work I need to have. So if you want to put this amount of work in right here, then you're done and you don't need to upload anything for me after your quiz. Now we're asked to calculate the delta G of the reaction for this reaction, given this information. Now this is akin to Hess's law. And There's one or two of these in the e-text if I'm not mistaken, but I wanted to make sure that we worked one together here. So if we're going to calculate this delta G, just like when we're using Hess's law, we need to look at this as a target. So here is my target. And remember, I can manipulate these equations, and if I flip it around, then I have to change the sign of the delta G. If I multiply through by a coefficient, I have to multiply my delta G by a coefficient. All the same rules apply. So here I'm looking at having calcium carbonate on the left side, on the reactant side, which means I need to flip this one around. And if I do that, I'm just going to write that over here. Calcium carbonate reacts to form calcium plus CO2 plus 1/2 O2. Then what I do is I change the sign of this delta G. So this delta G is now a positive 734.4 kilojoules. So now I have my calcium carbonate on the reactant side. Now I need to have a calcium oxide on the product side, but I only need one of those. So I'm going to multiply this entire reaction through by 1/2, and that actually multiplies my delta G by 1/2 as well. So now I have my calcium plus 1/2 oxygen reacts to form calcium oxide, and then I multiply that delta G by 1/2, so now I have a negative 603.3 kilojoules. When I add my reactions together, I'm going to cross out the like parts, and I should be left with my target, and I am. So now I'm going to add up my G values. And when I add up those G values, I get a delta G of the reaction is a positive 131.1 kilojoules. So what would we do for the work here? Well, I'm going to start by copying and pasting my reaction scheme in. And I'm just going to rearrange as I rearranged before. Take this arrow over. Looks like I missed a parenthesis here. That's not a parenthesis. And when I do that, then I change this sign here, and then I multiply this through by 1/2. So what I'm going to do is I'm going to give it some square brackets. Times 1/2. And then I'm going to change this value here to 603.3. And then I take and I'm going to copy my target value, copy my delta G, and say, oh, I have to take off the subscript, say that that's equal to a negative 131.1 kilojoules. That's all the work you need to show there.